So let's talk about how geologists know what the crust is made of. Remember that the continental crust has an average composition that we say is intermediate. It's actually a little bit maybe more felsic than that, but to first order we can call it an intermediate composition. And the oceanic crust, in contrast, is almost entirely mafic in composition. I should also note that one of the characteristics of the continental crust is that it's highly variable in composition. It's got rocks ranging from felsic all the way to ultramafic. It's got sedimentary rocks. It's got metamorphic rocks. It's a total mishmash with an average composition of this incredibly variable stuff that's approximately intermediate. And in contrast, the oceanic crust is almost entirely made up of just one composition, that is mafic rock. It doesn't have anywhere near the variability that we see in the continental crust. So the question I want to ask and answer here in this video is, well, how do we know that? And it turns out for the crust that we know its composition really well, and some of the reasons are kind of obvious. So first one I'll list is probably the most obvious, is that we can simply look around, right? We live on the crust, and so we can inspect the kinds of rocks that are under our feet, and we see indeed on the continental crust that they consist of a wide variety of rocks with kind of an average composition that might be something between silicic or felsic granite and intermediate diorite. Now in the case of the oceanic crust, it's a little bit more difficult. We can't in fact look around, and actually the actual composition of the oceanic crust was elusive for a long time until we developed, or actually had the interest to actually go around and start scraping rocks off the bottom of the ocean in a systematic way and putting drills into the ocean to extract rock and take a look. And we did that starting in the 1950s, and it was discovered, much to the astonishment of geologists, that in that case when we looked around we saw almost entirely one rock type, that being the mafic volcanic rock basalt. But once again, we gathered that information from basically looking at what was available on the surface. Now the second thing we can do, and we do a lot on land, is we can look at the results of boreholes and wells. So every time a well goes into the ground, either to extract water or perhaps to extract oil and gas, or simply an exploration well, geologists are required to record what they found in the process of going into the ground, record the kinds of rocks that they turned up as they drilled through them. And there are lots and lots and lots of wells and boreholes all over the earth, and concentrated generally in certain areas. For example, if we look at sort of a map of boreholes or wells in Louisiana on the left and Colorado on the right, you can see that these states are riddled with wells and boreholes, and each one of these wells and boreholes provides information about the kind of rocks underneath that area to a depth of perhaps several kilometers, maybe 3 or 4 kilometers. The very deepest borehole ever installed went down to a depth of over 12 kilometers. That was in Russia. It was an exploratory, a scientific borehole. Really was no reason to put it in there except that we wanted to see what was down there. So in general, that's the maximum. So although this is useful, these are always going down to a depth of no more than, at the absolute maximum, 12 kilometers. So on the continents, remember that the thickness of the continental crust is sort of on average about 30 to 35 kilometers. So this is even less than half of the continental crust. So even under our best case, where we can stick a borehole down over 10 kilometers, we're still only able to directly sample through boreholes the uppermost half or so of the continental crust. There are some wells, some kind of drill holes put into the oceanic crust as part of the deep sea drilling program, and that has proven fairly interesting, of course, but one of the results that came from that study of the oceanic crust was that they were uniformly coming up with mafic rock, mafic rock, mafic rock. So we don't really need to have 1,000 boreholes to tell us that the oceanic crust is almost entirely made up of a single rock type, mafic rock. Now fortunately, there are a few other pieces of evidence we can use to learn about parts of the crust that are deeper than about 10 or 12 kilometers. And one of the most useful is to look at rocks exposed on the surface. I'll just put rocks exposed via faulting. And what I mean by faulting, a fault, let me just write this down here. A fault is a break in the earth, a surface along which rocks have been displaced. And so what we find is, especially in mountain areas, if this is the surface of the earth here, that in many places there is a break, let's call it like this, along which one side has been shoved up in towards the surface. And so the rocks we see on the surface up here were originally formed perhaps way down here at some great depth, and they've been shoved up along this fault, and then erosion has exposed them where we can pick them up today. And that's why if we walk around in places like the Appalachians, it's possible to pick up pieces of granite, for example, which we know must have formed 10 or so kilometers down beneath the surface, but today they're found at the surface thanks to the action of the geologic action of movement along these faults. So the faults sort of are Mother Nature's way of shifting material up to the surface, shifting materials that form deep underground up to the surface where we can expose them. And that's a very valuable task that Mother Nature does for us, because that gives us samples of some rocks which form deep in the lowermost crust. Now, there's a couple other things that we use as well, and I won't talk a lot about them because there are separate videos on them. One is we can look at crustal xenoliths. Those are rock fragments that are brought up by volcanoes. They're discussed in a separate video, but remember that some of these xenoliths come from the crust, and if we can determine they come from the crust, that tells us what kind of material lies down there. An awfully big source of information as well comes from seismic wave velocities. Seismic wave velocities are really one of the best ways to infer the composition velocity. I can't multitask here. To infer the composition of rocks far beneath our feet, places that we can never sample directly, but we can still look at the seismic wave velocities and make inferences about the kind of rock that must exist there. And that's subject to, both of these are explained in a separate dedicated video you should watch to understand them. Finally, I want to mention one other important source of information, and that is with regard to the oceanic crust. The oceanic crust, remember, is much thinner than continental crust. Oceanic crust averages maybe 7 kilometers or so thick. And in fact, there are places on Earth where, via faulting, like I described before, not only do we see pieces of the crust, but under certain special circumstances, we can get the entire entire oceanic crust exposed along a fault. So for example, this boundary in blue here would be the Moho. The fault surface I've shown below, I'll give it a different color. So the fault here along which this huge block has moved up is actually shown here in pink. Okay, and that tells us then that all of this rock here, this is the entire thickness of the oceanic crust, and it has been pushed up, and erosion has revealed it along the surface of the earth. So we can actually go to places like Troodos in the Mediterranean, Troodos ophiolite in the Middle East, or we can go to Cyprus in the Mediterranean and actually walk along the surface. Here's my little person here walking along the surface. Here I am, and I'm actually walking over all of the oceanic crust. I can see it from the very topmost parts of the oceanic crust, which is covered by sediments, all the way to the very bottom of the oceanic crust, which consists of plutonic or coarse-grained mafic rocks. And so I have a really good way to inspect the entire thickness of the oceanic crust along these very special exposures that have a name. They go by a name called, these are called ophiolites. So ophiolites, which are fault-produced exposures of oceanic crust, provide a lot of information, a lot of direct information about the composition of the oceanic crust. Such a thing doesn't exist for the continents, right? That the continental crust is much too thick to be exposed along one fault like the oceanic crust is. So the continental crust is a little bit more difficult. Certainly the deeper parts of the continental crust are a little bit more difficult to understand. In contrast, the ophiolite sequences here give us really good direct information and confirm what we already thought we knew, which is that the oceanic crust consists monolithically uniformly of the mafic igneous rock, largely basalt near the surface, and gabbros deeper underground, but it's overwhelmingly mafic in composition. So that's how we know the composition of the crust.